Hi there. My name is Ellie Dunkle, and I'm a master's student at Oregon State University in the Coastal and Ocean Engineering Department, and I'm also an affiliated member of the Pacific Marine Energy Center, or PMAC. My undergraduate degrees are from the University of Rhode Island in ocean engineering and Spanish language, and I'm currently doing research with my advisor, Dr. Bryson Robertson, on wave energy resource assessment, wave energy potential, and applications of this on the west coast of the USA. This summer, I did some work completing a wave resource assessment of the PacWave wave energy test site off the coast of Newport, Oregon, which is in the central coast of Oregon. And it's comprised of two sites, the north site, which is smaller and not connected to the grid, and the south site is a bit larger, further offshore, and more representative of a harsher ocean environment. It is permitted and connected to the grid, so it provides a good opportunity to test wave energy converter devices. And the following slides are going to be results from PacWave South, as that is expected to be online and open for testing, hopefully in 2022. This map shows where data has been collected in the PacWave region. Data at North and South have been recorded as part of a hindcast model created by the Pacific Northwest National Lab, or PNNL. And PMAC has previously recorded wave data at PacWave South from 2014 to 2015. The goal of this work was to complete a technical specification of the wave energy resource according to the International Electrotechnical Commission, or IECE standards. And they say that the wave energy resource can be described by these 7 parameters, which are derived from the wave energy spectrum: significant wave height based on the energy spectrum, energy period, which is the characteristic wave period based on moments of the energy spectrum, omnidirectional wave power, maximum directionally resolved wave power, which is just omnidirectional wave power resolved to a direction theta. And you can see that's in another parameter that's necessary for the IEC specification. Spectral width, which describes the makeup of the sea state, and directionality coefficient, from which we can determine how spread out the direction of the wave field is. And environmental conditions are also supposed to be taken into account where relevant. So this could look like doing a general description of an ocean current profile, wind profile, or sea ice, if that's in your region of concern. The model created by Wu et al. At PNNL was chosen as a source of data for this assessment, and they created a hindcast model outputting 32 years of wave measurements with low error when compared to physical data. Their model uses WaveWatch 3 and SWAN models coupled, and they are both forced by CFSR to output the 6 variables you see in the yellow circle, from which we can calculate the last variable necessary for this bug. This figure shows a bivariate histogram showing the annual average frequency of sea states in terms of significant wave height and energy period. And the sea state with the greatest percentage of annual energy is found at an energy period equal to 10.5 seconds and a significant wave height equal to 2.75 meters, which occurs on average 227 hours per year. This histogram also shows the most frequent sea state occurrence, regardless of its energy output. And we can see that that's right here and occurs for 527 hours on average per year. And this is important to know for not only people interested in the sea states off the coast of Oregon and the PacWave region, but also so that wave energy converter developers can know what kind of sea states they're dealing with and how long and often these occur on average per year. Figure 3 shows a wave rose depicting the direction and magnitude of the maximum directionally resolved wave power relative to 0 degrees north. We see that the largest amount of this power comes to the west and northwest directions, so fairly perpendicular to shore. Figure 4 shows the variability of the mean direction of this power, and we see that it fluctuates between 270 and 290 degrees, confirming the results that we see in the wave rose, and indicating that the wave directionally resolved wave power is pretty narrow banded in this region. Figure 5 shows the variation of monthly mean of significant wave height. And these are minimum in the summer and maximum in the winter, which is expected since more storms occur in the wintertime. Energy period is shown in figure 6 and also decreases in the summer months and is maximum in the winter. In the summer, waves are more often forced by local winds. And so that induces high frequency waves, which are indicated by the lower wave periods compared to the winter times. We see in figure 7 and 8 that both types of wave power, omnidirectional and directionally resolved, are maximum in the winter due to those increased storms, and minimum in the summer when the sea is less energetic. The mean values of wave power in the summer are more steady, whereas the winter values are more varied, and that's again due to the storms. And since there's, as we indicated, a narrower field of directions that this wave power stems from, the maximum directionally resolved wave power is on par with the values that we see for the omnidirectional counterpart. Figure 9 describes the directionality coefficient, which is seen at a maximum in the winter months. So that means that the wave field converges to fewer directions during the winter. And we think that that's due to the storms that are more present in the winter times come from a more concentrated direction. Lower coefficient values in the summer are due to a wider wave directional field, and that's due to those high frequency wind-induced waves. In figure 10, we see low spectral width values in the winter months, and that's due to the swell or storm dominated energy spectrum, which narrows the peak of the energy spectrum. This value increases and goes toward a value of 1 in the summer as the wave field becomes more varied, and that's again thanks to the high frequency wind dominated wave field. Outside of the IEC spec, we analyzed sea states that gave favorable operation and maintenance, or O&M conditions. And this was to provide WEC, or wave energy converter developers, with an idea of when they'd be able to work on their devices, lay cables, and do things of that sort. So full days with measurements of significant wave height less than 1.5 meters and a peak period greater than 8 seconds were what we chose to define favorable sea states. Figure 11 shows the total average amount of days allowable for one-day O&M windows, and 848 of these were seen throughout the time period. Figure 12 is a box plot, which allows for us to get a more comprehensive look at the data indicating the satisfactory sea state occurrences, and we see that the maximum amount of days per year for O&M in the summer months ranges from 6 to 8, with minimums of at least 2 days per year on any given year. And sometimes O&M endeavors require larger windows of time because they need more time to lay cables, do maintenance, again, things of that nature. And for this purpose, 3-day windows were analyzed as well as 5-day windows. We see in figure 13 that August has the most favorable conditions for these 3-day windows. Again, the summer is pretty calm at PACWave relative to the winter. And figure 14 shows in May that May through September may have anywhere between 0 and 3 windows during any given year. 5-day windows were scarce, and on average, a 5-day window will not occur at PACWave. And to do a general wind description of the PACWave site to stay in line with the IEC recommendations, we analyzed data from these 3 NDBC buoys, which are National Data Buoy Center stations by NOAA, shown in figure 17. Figure 18 shows a description of the wind data gathered by means of a box plot, and median values for all 3 stations were between 5 and 6 meters per second. The data from NDBC 46097 was closest to PACWave, and so we used that for further analysis. A histogram of the wind speed probability at this station is fitted with a Weibull distribution fit in figure 19. And the Weibull distribution, as we know, is expected to well describe wind speeds, which it does in this case, and shows that wind speeds between 3 and 7 meters per second are most likely to occur at 4.5 meters above the sea surface at the PACWave location. As expected based on previous analyses in the region, the winds come predominantly from the north and south, as we see in the windrows in figure 20. So although this is a lot of useful information regarding the resource, this IEC method can sometimes introduce uncertainty because additional environmental conditions are not always adequately taken into account. And research shows that environmental conditions play a role in the amount of wave energy resource available for wave energy converters to convert into usable energy. And additionally, researchers have found that analyzing the wave field in greater detail increases the fidelity of assessments. So more accurate predictions may be made in power prediction or more in-line tension prediction if they take environmental conditions into consideration. So right now I'm working on an ocean current and tidal water elevation description at the Packwave sites. And teams are also working to deploy SOFAR spotter buoys that will provide physically measured wave data at the Packwave locations. And in the future, I think an increased detailed environmental modeling of additional ocean processes at Packwave would be very useful to determine a comprehensive view of the energy available with minimal error at the test sites. So thank you for your time, and thank you, John, the president of COPRI at OSU, for asking me to create a video. If you're interested in reading the assessment in full, you can find it at the OSU Scholars Archive, and you can Google Packwave resource assessment. And yeah, thank you for your time, and thanks for stopping by.